I'm now going to show you another example of a separable ODE, and this is one that actually has applications in the context of growing populations. It's called the Logistic Model, and again, I will discuss first of all where it comes from in terms of an application of growing populations, then how to solve it, and then make a few comments about what that solution looks like and what it means. Now remember that assuming that certain things are true for a growing population, then the way in which this population grows can be described by this exponential model, which says that the rate at which the population grows is proportional to the size itself of the population. And in this case, of course, y being the size of the population is going to be a function of time t. Now, that equation, however, relies on a number of assumptions, and which may or may not be true. And the one which is most easily seen as unrealistic is the fact that this model requires the population to have the ability to grow indefinitely. It can grow as big as it wants. Remember, the solution is an exponential function. So not only is it going to grow indefinitely, but it's going to grow faster and faster. This is a very unreasonable assumption. So what we're going to do is we're going to make a little bit of a change on that assumption in order to make it a little bit more realistic. So what are we going to do? So we're going to assume that the population actually has some kind of a maximum size that it can reach. So it cannot go beyond that size. So basically for whatever limitation coming from food, space, or whatever, or predators, or whatever it is, there is some reason why the population cannot get any bigger than m. Okay? Then we're going to assume also that as the population size gets closer and closer to this maximum m, the rate of growth will slow down. Okay, so as it gets closer and closer to the maximum, the population will become more and more stable. So in order to do that, we're going to change our equation a little bit and change it to this one. So y equal ky times 1 minus y over m. Okay. By the way, the m is often called the carrying capacity or the maximum capacity of the population. Now, notice again, this is a very simple and small change to the original equation, but what does it do? Well, if this population, or as long as the population size y is much less than the maximum m, that's what that double less symbol means, then y over m is going to be a very small fraction. So y minus y over m is practically going to be equal to 1, and therefore the equation reduces to y prime approximately equal to ky, which is our usual exponential model. So as long as the population is much smaller than its maximum capacity, then the process will look very much like an exponential process. Okay. However, as y gets closer and closer to m, then y over m will become closer and closer to 1. Therefore, the quantity in bracket will become approximately 0, and then it doesn't matter what else the rest of the equation is, that right-hand side will be approximately 0, which means that as the population approaches its maximum size, its rate of growth will decrease to 0 and it will become stable. Okay, so that's exactly what we wanted to model. So let's see what happens when we have this kind of situation. So again, this is a logistic model, and notice this is a separable ODE. How do I know that? Well, the independent variable time is nowhere in sight, right? So I can easily separate by putting all the y's on one side, and then on the other side I'm going to end up with a constant. And that's exactly what I'm going to do right now. Okay, so I can separate the variables easily, right? Dy by dt is equal to, well, just a little change in the bracket just to make it algebraically more workable. And then I'm going to separate the two variables. It's going to look like this, right? You may want to pause and make sure that you're convinced that the algebra is correct. Okay? So now we have all the y's on one side and the t's, well, actually there isn't any, just the dt is on the other side. Well, let's see what we can do with that. Now, we have our original logistic differential equation. We have changed it to look like this. It is separated. Now what we're going to do is on the left hand side, notice that we have a rational function. Remember, m is a constant. So we have a rational function and we need to split it into partial fractions. Well, it turns out to be fairly easy. I'm going to leave it to you to check that in fact once you use your usual partial fraction technique, this ends up being split as 1 over y plus 1 over m minus y, which is quite nice. So both of the coefficients equations on top are both 1s. Okay, so we can write that differential equation. Actually, we can integrate both sides of the differential equation by writing the left-hand side in the partial fraction decomposition. All right, so we can integrate. Well, the left-hand side is very easy. We end up with the sum of two logarithms, and the right-hand side is even easier. It's just kt, and let's not forget the plus c. All right, now this is an implicit solution, right? So what we want to do is get an explicit solution for this equation. Okay, we don't want to do everything implicitly when it comes to populations. We want to be very explicit about them. All right, so we're going to rearrange, assuming that y is going to be somewhere between 0 and m. It cannot be 0, otherwise we don't have a population, and it cannot be m because that would be the maximum value towards which we are reaching. So we're assuming that it's somewhere in between. By the way, if y becomes equal to m, then the function becomes also the left-hand side of the differential equation becomes undefined. Things become messy. So we'll forget about that. If you want, as an additional exercise, you may think about what happens if y is greater than m? Can I still solve that equation? And actually, it's an interesting exercise, and I'm sure you'll be able to do it. Now, let's rearrange. What we can do is we can combine the two logarithms on the left-hand side into the logarithm of a fraction. And if you're wondering about what happened to those absolute values, remember, I'm just assuming that y is between 0 and m. That means everything there is positive. Okay, so I don't need the absolute value. So I now have logarithm of that fraction is going to be equal to kt plus c. And now what I'm going to do is I'm going to eliminate the ln, of course, by using exponentials on both sides. And so that leaves me with that fraction being equal to e to the kt plus c. I'm taking the exponential. Now I can rewrite that also as e to the kt times e to the c. Now e to the c is an arbitrary constant, actually an arbitrary positive constant, but then again we are dealing with positive numbers, so that shouldn't bother us. So instead of carrying it all along as e to the power c, I'm just writing it as capital C. Okay, so just to simplify the notation. All right, let's move on with some more algebraic steps. Okay, so at this point, this is already an implicit solution. Again, it's a slightly easier implicit solution than the one we had before, but it's still implicit. We want to make it even more explicit. So let's do this. Let's multiply left and right hand side by the denominators. We get rid of the denominator. I'm going to go a little bit fast on the algebra. You want to pause and check that you get it right and that you can follow it. Then I'm going to rearrange this equation now, which is now a linear equation in y. So I'm going to collect all the stuff with y on the left hand side, the constants on the right hand side. And finally, I'm going to divide by the coefficient of y in order to get our solution. All right, notice that the c that we have in this formula, remember in the exponential model, the c that showed up was actually the initial amount. Okay, in this case it is not. If you put t equals 0, you don't end up with y equals c. Okay, so c is not the value of the population at the beginning. What is it? Difficult to figure it out. It's going to be a lot easier if we write this equation in a different way, which is going to then have a better interpretation. The way we're going to do it is we're going to let a equals c to the negative 1. Remember, c was an exponential, so it cannot be 0. So I can take the reciprocal of a. Now in this situation, negative 1 is just the reciprocal. C is a constant. Okay. So what I'm going to do is I'm going to call a the reciprocal of c, and I'm going to multiply top and bottom of that fraction by a times e to the minus kt. Again, you may want to pause and do the algebra on your own before I show you what happens. If you do that, then the equation becomes y equals m over a e to the minus kt plus 1. Okay, first of all, this one is easier because it only has one exponential piece, okay, and also has m all by its glorious self on the numerator. But not only that, but that a that we have constructed, that a actually has a special meaning. Okay? It has a special interpretable meaning. Okay? So what I'm going to do is I'm going to let you try and figure out what that a represents. Now remember that I just said a minute ago that c is not the initial value. Well, guess what? A has something to do with the initial value. Okay, so try to interpret a in terms of initial values and see if you can figure out what that means. And I'm going to leave that to you for fun. And then that will tell you how this particular solution is a solution that can be used in practice to generate logistic models for growing populations.